So this figure shows that, the slide shows that with the phasor representation, the time domain response of impulse response within the transmission line circuit can be transformed into a frequency domain response, which can be represented by using a phasor expression, and it can used to represent the behavior of using a continuous sinusoidal input function. So because this representation is an infinite series, and we can write up the analytical solution of this equation. So now we have this this result. Note that the exponential on the denominator and numerator are purely imaginary. They are exponential function with purely imaginary indicator over here. So they are the magnitude of the exponential function on the denominator and numerator are equals to 1. The magnitude itself is equals to 1. All right. So the magnitude of this function, is determined by the selection of frequency. It's determined by the frequency omega. When the frequency omega satisfies this requirement, that is 2 omega times T2 equals to 2m pi, where m are positive integers, then the value of this thing becomes 1. Becomes 1 in the denominator. Becomes 1 in the denominator. As a result, the denominator becomes 1 minus 1 over 9. So the result, the magnitude of this overall expression is 0.5. The magnitude of the equation is 0.5 when omega equals to multiples of pi over T2. On the other hand, when omega equals to 2m plus 1 times pi over 2 times T2, that is the odd integer of the, which result in pi, 3 pi, 5 pi, or odd integer of pi, and as a result, the value of this exponential becomes minus 1. And the result of 1 minus 1 over 9 times exponential blah blah becomes 1 plus 1 over 9, which is 10 over 9. And as a result, the magnitude of this function becomes 0.4, which is the possible minimum number of this equation. And so as, to put it in short, that is, when when this value 2 times omega T2 are even number for even integer number, you have minus 1 over 9, and it's odd number, you have 1 plus 1 over 9, and they will reaches the maximum amplitude and minimum amplitude respectively for the two conditions. And for other frequency, for other omega values, the magnitude will vary in between 0.5 and 0.4. So here is a drawing showing the response. So now that in the horizontal axis you have frequency, you have omega, angular frequency. So and here is the case for pi over 2 times T2, so you get 0.4. When it becomes an even multiple of pi over T2, that is 2 times of pi over T, 2 times pi over half 2 T2, right? So you can see that this odd multiple, and here are the even multiple. So you have a 2 over 2, 4 over 2, 6 over 2. So at multiples, you reach the maximum number, 0.5, and in odd multiple of pi over 2 times t2, you reach the minimum value. And so the vertical axis is the magnitude of the output voltage, all right? Another thing you should note here is at a DC condition, that for an incident wave of very, very low frequency, you also reaches maximum 0.5. So the conclusion of this analysis shows you that for this three-section transmission line problem, the output voltage that is reaches to the right end of the transmission line shall varies as the frequency change. 所以不同的输入频率信号在这一个三段传输线的传播过程当中，它能够透射出去的总量，透射出去的总量，当然这是一个 steady state 稳态的一个过程，也就是说你用一个特定频率的电磁波持续给它做一个有左往右的传播的时候，它到右边的穿透量会随频率变化。有的频率呢，它穿透量是比较大的；有的频率的穿透量是比较小的。而这个东西呢，其实跟什么有关？其实跟你的那个传输线的长度有关，传输线的长度有关。那这个 for this three-section transmission line case, one interesting example is the so-called radon. Okay, well, do I have a radon over here? Okay, radon spells like R-A-D-O-M-N. So it's it can be you can think of it radon 洞。洞现在大家比较熟了嘛，那个什么巨灯一个球形的罩子就洞嘛，照在雷达上就叫瑞洞 ，OK， 好，所以这边你看到的东西啊，这个都是瑞洞。现在的那个战机，它前头都是打开来这种叫做 ELSA 还是 ASA。有源或无源的相控阵列雷达了然后前面，所以飞机的这个东西它其实只是一个塑胶罩不是塑胶材料的罩子把它盖起来了那像这种大的球形呢，里面就是一个转的碟子了Okay, so the objective of radon is to protect the antenna. However, at the same time, it should not interfere the operation of the antenna within the radon. So, one design criteria is the radon should minimize its perturbation for the operation of the antenna. So the objective is to make the radon such as it does not exist. 所以就是说我们事实上在这个天线的外面摆了一个塑料盖子。那么你从电磁波传播的观点中，你会发现电磁波从空气跑到塑料盖子，再跑到空气，它有一个材质的变化。它有什么？有本质阻抗的变化。空气的传播，你的本质阻抗 intrinsic impedance 是377欧姆，但雷达罩一般是塑胶盖子塑胶材质的，它的本质阻抗，它的 dielectric constant epsilon 不等于空气，所以它的 intrinsic impedance 跟377欧姆是不一样的比377欧姆小。那雷达罩外面呢，又是一个空气又不是377欧姆，所以它跟我们前面看到 example 6.3 的那个 three-section transmission line 是一样的问题那有没有可能让它做的好像是那个雷达罩好像是不存在的答案是可以但是你要去 想想看哈，为什么可以做成这个样子哈。For reflection and transmission of uniform plane wave incident normally onto the dielectric slab, the arrangement is equivalent to the three-line cascade, as we have seen in example 6.3. And because the characteristic impedance in the three material free space, the polymer, the radon material, and the free space are not the same. So what can we do to minimize the interference, minimize the reflection? Now, so what we can do is this. So we know that the equation is subject to the change in the frequency, omega, which so the lowest frequency for which the dielectric slab is completely transparent is at this frequency. Now, so supposing that for a very low frequency wave, the transmission of the output signal is in fact 1 注意到前面的时候在那个 case 里头，我们这边写的是 0.5 跟 0.4 嘛那个 0.5 的原因是因为你的那个传输线的那个传输线电路的左边的那个 generator 端的那个讯号源端，它因为内部的分压公式的关系，所以你变成 0.5 当然，假如对于空气来讲的话，它的那个入射讯号我们可以把它视为单纯的完整的入射讯号的话，这边就变成1所以事实上那一个变化图在这边看起来会变成是1到 0.8 之间所以假如你的频率非常低的话，其实那个雷达罩看起来其实是透明的也就是说，当你的波长比那个材质不连续材质的厚度大很多很多的时候，那个不连续就变得无关紧要，不重要所以低频的时候它是 transparent， 但当频率升高的时候，你的那个雷达罩的那个厚度跟你的那个波长比值接近的时候，它的传输线效应就跑出来了。所以这一个图会告诉你，它在不同的厚度的时候，或者是说不同的频率的时候，不同的波长的时候，它有的时候你的那个雷达罩可以是透明的，没有影响的但有的时候呢，它又会被讯号会被减弱我知道这一点或许你现在没有办法那么容易接受不过我们慢慢看我们到后面还会补充更多的证据了Alright, so according to the plot, the lowest frequency the solution of lowest frequency should be at this place. That is, the frequency omega equals to pi over T2. Now that T2, which as the name suggests is a time delay. However, the time delay is associated with what? It's associated with the thickness of the radon, the length of the transmission line. So we can substitute T2 as the length, that is, as the time required to go through this plastic material. So that is the length of the radon of the second section of the transmission line over the propagation velocity of this material. So we can have this result over here. And to simplify it, we can substitute, we can take C over square root of epsilon r and mu r as Vp. That's the propagation velocity within the material. And divided by 2 times F. And if you substitute Vp as frequency and wavelength, that is Vp equals to frequency times wavelengths. Then it can be simplified as lambda over 2. So the result is if the radon thickness, if the thickness of the second transmission line section happens to be half of the wavelengths, then the existence of the radon will not perturb the propagation of the incident wave. All the incident wave, all the incident energy will go through the radon and reach the other side, which suggests the radon itself seems do not exist. 所以听起来或许不太容易接受啊，也就是说，在满足这个条件情况底下，你的入射电磁波，即便它有遇到阻抗的不匹配，有注意到材质的不连续，但是所有的能量都还是能够穿过这一个雷达罩，这一个第二段的那个传输线啊。而这个答案其实不是只有一个，这个只是最薄的雷达罩了。它其实这一个答案，这一个答案，后面那几个答案都能够满足 transparent 透明的这一个条件只是说后面那几个答案随着它的那个 propagation delay 的那个增加了或者说频率升高，它的那个厚度有那个厚度会越来越大所以就是说第一个答案是波长的1半，那第二个答案呢波长的1倍，第三个答案呢是波长的1.5倍这些都能够满足这个条件所以这边 here is an exercise, a radon made of polypropylene, which has a relative permittivity of 2.25, is used for an X-band radar that is about 10 gigahertz. Find the thinnest radon thickness applicable for this radon design. So this is the radon looking from the inside, and here's the radon looking from the outside. This is the radon looking from the inside. So you are supposed to have rotating antenna within the radon. So substitute the given condition, that is epsilon r equals to 2.25, which ends up propagation velocity of 2 times 10 to the 8th, because propagation velocity in free space is 3 times 10 to the 8th, and the square root of 2.25 is what? Is 1.5. So you only have 66% of the propagation, the propagation speed in free space. It's 2 times 10 to the 8th. And considering the frequency is 10 gigahertz, so the wavelengths will be 2 times 10 to the 8th divided by 10 to the 10th. Okay, so you got the result. The wavelength is 2 centimeter, and which ends up with a radon thickness of 1 centimeter. It's a thin plastic material. Okay, and it looks transparent for the incident electromagnetic wave. And here is this figure attempts to show you how these things happen. How this thing happen. So again, we use the technique similar to the bouncing diagram technique. It's usually referred as ray tracing 射线追踪法。这我们在天线设计然后电磁波的那个传播分析里头常用的一个方法叫射线追踪法那事实上你可以看到它跟 bouncing diagram 是类似的So here we have an incidence, and at this interface you will have a reflection because the difference in the intrinsic impedance. So here is the first reflection term. But at the same time, the rest of the energy goes into the second transmission line. So this represents the energy goes into the transmission line. And some of the incident energy that reaches this end is still transmitted to the other end, okay? But for the analysis right now, we don't care about it. We just focus on the reflection part. So we know that some of the energy reflected back, and some goes to the left-hand side. Of course, some continuous, like this one, some continuous to the other propagation direction. And some of the energy are reflected. And this analysis, this ray tracing technique can be conducted continuously, so you have an infinite series, all right? So back to the first three terms. We know that the magnitude of the first three terms is proportional to the reflection coefficient. The second term, this is actually what? This is actually the transmission coefficient tau, okay? Reflection coefficient gamma, tau equals to 1 plus gamma. So this is actually the transmission coefficient at 1-2 interface. How about this? Minus gamma. This is the reflection coefficient at 2-3 interface. Remember that here we have free space, dielectric, and free space transmission line. So the reflection coefficient looking from free space to dielectric is gamma, and the reflection coefficient looking from dielectric to free space shall be minus gamma. Okay? So this is the transmission coefficient at the first interface. This is the reflection coefficient at the second interface, and 1 minus gamma is the transmission coefficient at the first interface. So all the components, all the things happen at the interface can be recorded in terms of transmission coefficient and reflection coefficient. So you can continuous for the third term, fourth terms, fifth terms, so on and so forth. So again, you see that this is an infinite series. So if you write out the infinite series, you can write up an analytical solution of this infinite series. And magically, if you choose L equals to lambda over 2, note that there is one thing that we didn't focus, or we didn't indicate in this derivation is the propagation delay in terms of the phase change in the transmission line. Note that we choose the length of the radon as lambda over 2. What is the significance of lambda over 2? Half reference. Half reference suggests the propagation, the phase change in this propagation is 180 degrees. And note that the following terms, the second term goes to the right and bounces to the left, so it has a round trip propagation delay. It's a 180 degree one way, so that will be 360 degree round trip. And exponential of J2 pi, that is 360 degree, equals to what? Equals to 1. Okay, so under this condition, the following terms are adding up with the first term constructively. So you don't have to worry about the phase change accumulating this bouncing back and forth passes. So under this condition, you found out the resulting analytical solution for this infinite series happens to be gamma. So you have gamma minus gamma, and it becomes 0, which means you don't have reflection. But now that this is a phenomenon happen, this is the overall observation. of the entire process。也就是说，巨观的状况底下，你有一次的反射，弹一次的反射，弹2次的反射，弹3次的反射，弹4次的反射，这些东西加起来之后，它的效果等于反射为0。但是假如你微观的，你只在这边看一下，有反射嘛，这边也有反射，这边也有反射，都有。微观来讲，因为你界面不连续，主看不匹配，所以你有反射。反射是不为0的，微观来讲。但是 overall 把它加总整体来看的时候，它的反射量是0的。那既然反射量是0，那透射量呢？注意我们这边给的是 free space 会不会消耗能量？不会。Perfect dielectric 会不会消耗能量？不会。所以能量守恒嘛。既然你反射总体看下来，总体观察下来，反射的能量为0，那透射的能量呢就为1嘛。所以当然你也可以把这个分析在右边再做一次就是说。这边是第一个出来的项，这个是第2个出来的项，第3个出来的项所以你也一样有一个无穷级数、无穷等比级数。你会发现这个无穷等比级数在这边所收集到的它是等于1的但这个状况的成立的先决条件是这个长度是半个波长。假如它是1/4个波长的话，会发生什么事情？1/4个波长，还记得前面那个斗上下斗的图吗？1/4个波长的话，它会在中间是那个最低点。意思就是说，这一项，假如1/4波长的话，它弯位的 propagation delay 是几度？90度嘛，one trip 嘞，90度加90度等于180度。意思就是说，这一个，假如你是1/4个 lambda 的话，那这一组的讯号你前面要加一个负号。这一组讯号是正的啦，因为它弹了4次，那个负号再乘负号还是正1。下一项呢又多了一个负号，所以它加起来的结果，就不会是等于0的，不会是等于0的，会是一个0到1之间的数啦，所以这一个雷达罩在微波频段看起来好像不存在这件事情，是做得到的，但是它只有在特定的频率在其他频率的话，你会看到还是有能量被反射，那透射能量就没有那么多了Alright, so that's the first case, putting into the multi-transmission line section. And here's another example shown in the textbook. It means the name of this technique is TDR, Time Domain Reflectometry 时域反射啦Time Domain 你知道嘛那后面那个字是反射的意思啦那就是我们在时域上面去观察传输线上面的一个状态那这个技巧在 TDR 叫做 TDR。这个东西的应用传统的应用呢，我讲一个简单的例子但现在已经看不到了叫做抓第4台断线以前台湾现在街景整理的比较好，但我小时候我指的是20-30年前的时候，其实台湾的那个街景很难看的，因为路上都有很多的电线但基本上它不是电力公司的电线你现在到越南到泰国还是可以看到很多路上都是一捆的那个黑黑的线，那个线不是电线所以你不用担心会触电，但它是那个 coaxial cable 第4台的缆线以前台湾有很多啦不知道现在乡下还有没有，现在比较少了现在很少看到，以前日本也还是很多了这种第4台缆线以前台湾只要遇到那个台风大概台风的灾情，第一个是断电当然现在那个电线大部分都移到地底下去了只是台湾最近的小动物都不太乖但以前的话就是台风完之后你会断电，还会断电视，因为第4台那个电视讯号会断掉。 那原因就是挂在那个路边墙上的那些第四台缆线断掉被吹断。那假如第四台的工程师的话，你要怎么知道我线断在哪里？所以这个技巧呢，就是来帮他们用诊断你的传输线上面哪些地方出现所谓的断线不连续所以它是寻找传输线中不连续的处的技巧。但你会知道说，当然我刚才讲说这是20-30年前的事情嘛就是第四台，当然现在第四台也还是会用这个方式做了但毕竟重要性看起来不是那么高的了但这个技巧还是很重要，它反而重要的地方跑到哪里去？跑到 IC 去了。也就是说你在做 IC 的debugging 的时候或者是说 IC 的那个 signal integrity 的诊断的时候那个晶片洗好，然后封装完你有听过良率嘛，对不对？那什么叫做良，什么叫不良？不良就是不会动嘛，不会动的话，你要去看说那个线是死在哪里反正我们同学里头应该有些成绩好以后可能会走 IC 组吧，对不对？IC 组的话，你硕班要念几年？可能比较久一点然后久的原因是卡在哪？卡在下线嘛，对不对？那你下线的时候，下线前后你就要怎样？天天吃斋念佛嘛，对不对？保佑你那个东西回来是对的。那比较不对怎么办？不对要看哪边不对所以他那个找线路断掉或者线路不对的地方用这一招 TDR OK。所以虽然你看起来你在讲的是电子传播其实整个大电机里头很多技术其实是相关的所以它现在 TDR 反而对于 IC 的那个状况的 IC 线路极为小的这种 IC 线路的那个，因为毕竟你不是眼睛可以看得到的嘛有时候封装下来你也没办法用那些放大镜显微镜去看它嘛所以只好用这种间接的技巧来去看找说你那个电路的断点不连续出现在哪个位置。Okay, so come back to the schematic of the TDR technique. So for the case shown, we have a system under test. It's the circuit to be diagnosed, which is made up of transmission lines. And you have a pulse generator. So similar to what we have in example 6.3, you have an impulse generator which provides impulse signal repeatedly. Pop, 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 pop. And here you have a display. That is oscilloscope. So oscilloscope is a time domain machine showing the voltage, mainly the voltage signals going on the transmission line. So it has a high impedance so that the probing of the scope will not affect the signal that goes within the transmission line system. And here is a match attenuator. What is the purpose of this component? This component is meant to absorb the reflected energy so that you won't make the circuit more complicated. All the reflected energy will be absorbed by the match attenuator so that it will not go back into the transmission line. Okay, so here's the basic component of the TDR system. So what will happen? What happened within this circuit? So first, the pulse generator will provide some voltage impulse, and you will use the oscilloscope, the display, to detect the reflected signal. The reflected signal. And the purpose of the match attenuator, the match attenuator, is to ensure that there's no more reflection goes back to the system, right? So the signal goes starting from the pulse generator, goes into the system. If it gets reflected, it will be detected by your oscilloscope. Okay, so let's apply the transmission line circuit here, example 6.4. So assuming we have a signal on the, we have this circuit, it has the length, the overall length of the circuit of the transmission line is 10 meter, and it has short termination at the end, and in between is 我这边写错了，不是串联电阻，并联电阻哈 ，a shunt resistor. In between is a shunt resistor of 120 ohm. Okay, so which places on the transmission line will provide reflection? Well, it will provide reflection if you have impedance mismatch. And the impedance mismatch is provided by discontinuous condition on the transmission line. So the first discontinuity is over here. So some of the incident energy will get reflected from this position. And here you have another discontinuity, that is the short termination at the right end. So later on, because it's placed further away from your source, so it will take more time for this reflected energy to reach the left-hand side. Okay, so if we apply, so let's begin our analysis about this problem. So supposing the duration of the impulse is 10 nanosecond, and the repetition frequency, that is the frequency of the impulse, is 10 to the fifth hertz, which means the period is 10 microsecond. If suppose that the propagation velocity within the transmission line is 2 times 10 to the 8th, 10 microsecond means the signal will go within the transmission line for 2,000 meters. And as the figure shows in the previous slide, you see that the overall length of the transmission line is 10 meter, which means so 2,000 meters is the period 10 microsecond is long enough for the signal to saturate within the transmission line system 所以这边看到的是脉冲本身是10个 nanosecond 10个 nanosecond 是维持多久？1个 nanosecond 是几公分？30公分的 propagation delay 但我们现在讨论的是在传输线里头的所以传输线里头的那个 propagation delay 会比较应该说波速会比较慢嘛所以我们假定1个 nanosecond 大概只能跑20公分所以10个 nanosecond 宽的脉冲大概会在里头跑2公尺也就是那个脉冲讯号在里头维持的那个长度大概是2公尺，而它的那个间歇的频率是10的5次方，也就对应到10个 microsecond 所以也就是说这一次的脉冲跟下一次的脉冲中间会间隔10个 microsecond 也就是说讯号可以在上面走2000公尺了那有2000公尺的相对于你的那一个传输线长度10公尺来讲是200倍所以里面的能量在这个传输线系统弹来弹去之后，其实早就应该能量就已经消耗殆尽了所以这一个间隔的频率了间隔的这个时间10个 microsecond 是足够长的了所以你会观察到，就前一次的那个 pulse 所打出去的能量，应该在下一次 pulse 出现之前就已经死光光了Alright, so let's begin our analysis using the voltage bouncing diagram. So here is the result. So you can calculate the amount of reflection using the bouncing diagram techniques. Unfortunately, I guess we probably do not have time to finish the discuss today. So I will continue about this on Friday. So let's